Okay, this problem is intentionally really, really tough, but it's because I'd like to develop a little bit of the skill of how to look at polar regions and figure out bounds of integration for them. So you'll have to forgive if there are a couple of mistakes along the way. This is like super, super detailed. First of all, we're told that this is a cardioid. Cardioid should make you think of the word cardiac, as in heart shape. So cardioids are things that look like this or like this. All right. Let's get a sense for what this cardioid looks like. 1 plus cosine of theta. When theta is 0, this will have a value of 2, because after all, that's too close. There we go. 1 plus cosine of 0 is 1 plus 1, which is 2. So the cardioid begins at that point. When theta is pi over 2, that's when it will be hitting the y-axis. And cosine of pi over 2 is 0. 1 plus 0 is 1. So it hits the y-axis at 1 right there and passes through that point. When theta is pi, cosine will be -1. So 1 minus 1, which is 0. That means that at pi, it actually returns to the origin. And now we can start to get a sense for the behavior of this thing. It will never have an r that is larger than 2. So the wrong way to start drawing this would be to start going like that, because this means that r goes from smaller values to larger values as theta increases from 0 through the positive first quadrant. And that's wrong. It's not going to do that. So it has to curve inward like this. It has to curve inward, and specifically, it'll do it like this. See how this is the way that guarantees that the 1 plus cosine theta begins at 2, tracks through decreasing values all the way through to 0. After it goes past 0, remember that cosine does the same thing in reverse in the second half of the unit circle as it did forward on the first half. So we should expect, and it does end up happening, that it passes through this point in exactly the same sort of fashion. Hang on, I'm going to give myself just a little bit more room with this, just because it's going to be a little crowded if not. Okay, so now we've got the cardioid drawn. Outside the circle, r equals 3 cosine theta. I want to give you a reason to believe that this is going to be a circle in the first place. R equals 3 cosine theta. If I convert that to Cartesian, it's root x squared plus y squared equals 3 cosine of inverse tangent of y over x. You may remember from your pre-calc classes that it's possible to write this by drawing a triangle and writing it in terms of x and y without any trig functions. So tangent inverse of y over x implies the existence of this triangle, where you have y over here, x over here, and this here is the angle, which I'll call alpha for now. Then this is the hypotenuse. Pythagorean theorem tells us that it will be x squared plus y squared in square root. The cosine of this then will be equal to the adjacent of x divided by the hypotenuse of root x squared plus y squared. So r equals 3 cosine theta turns into this. It's square root of x squared plus y squared equals 3 x over square root of x squared plus y squared. Multiply on both sides by square root of x squared plus y squared, and you get x squared plus y squared no longer in the square root equals 3x. Move the 3x to the other side. X squared minus 3x plus y squared equals 0. Complete the square on x. That means that we're going to be taking half of the -3, that's -1.5, squaring it and adding it to both sides. So x squared minus 3x plus 1.5 squared plus y squared equals 1.5 squared. This then becomes x minus 1.5 squared plus y squared equals 1.5 squared. And this is a circle with a center at 1.5 comma 0 and a radius of 1.5. So this is a circle. It's possible to understand why this is a circle. You don't just have to be told. But for the actual shape of the circle, we can reason it out based on that or based on the behavior of this polar function. When theta is 0, this is going to be 3. 3 times 1 is 3. When theta is, it's easiest to evaluate this just at the poles. So when theta is pi, what will this be? Well, 3 times, wait, no, actually, when theta is pi over 2, when theta is pi over 2, then you have 3 times 0, or 0. When theta is pi, this is tricky, but when theta is pi, r is negative 3. Now, we don't usually think of r as taking on negative values, but when it does, what it means is that you go in the opposite direction. So pi usually means that you go to the left. But in the case when r ends up being a negative value, that means you go in the opposite direction. So what does this mean for the case when theta is pi? It means that you actually end up just repeating this same location. Can r ever be, or can you ever pass into something other than the first and fourth quadrant? What you would need is for theta to be like some second or third quadrant value, and for cosine to be positive. But cosine is negative in the second and fourth quadrants. So we know that the circle is never going to enter those quadrants. The circle then is this sort of shape. And we want the region, we have drawn that now, we want the region inside the cardioid, but outside the circle. Okay, this itself is going to be complicated. I told you this would be hard. Let me see, I need to get rid of all this because we're not doing that right now. Okay. We're actually not going to be able to do this with a single integral, because if you zoom in, what this looks like is this. There's the circular region right here, but then there's also the cardioid that comes in like this. So I'm going to actually divide this into 2 different regions of integration. There's going to be this stuff, which you'll notice is only bounded by the cardioid. The circle doesn't enter into it at all. Then, separately, we're going to look at this stuff over here, because this is bounded by both of them. So if you try to do this with a single integral, you're going to fail. You're going to have to set up 2 different integrals that deal with the 2 limits of integration. All right, we're getting closer to the answer, but we also need to find some limits of integration. Notice that you can use symmetry a lot here, because this here is the same as this down here. If I call this area 1 and this area 2, area 1 equals area 2, and so it will be sufficient to find one of them and double it. For the same reason, it will also be sufficient to say if this is area 3 and this is area 4, then since area 3 equals area 4, we can just find one of those and then double that. So we don't have to worry about maybe what could be this intimidating jump over an axis, or like, you know, these are regions are like disconnected in some sort of way. We can find just one and we can calculate it like that. Let's do the one that's bounded just by the cardioid so that we don't have to worry about the difference between 2 functions, at least for now. So what is the equation of the cardioid. It is 1 plus cosine theta. Okay. And over that domain, theta goes from pi over 2 to pi. Now, think about this. It's like the hands of a clock. Pi over 2 is noon. And then it ticks down to pi by going this way. So that's exactly what's happening here. You're rotating through that angle. So you're going from pi over 2 to pi. So to get the area of the first region, we can say we're going to integrate 1 dr d theta over area 1. Area 1 is described by r going from 0 up to the cardioid and theta going from pi over 2 to pi. So theta goes from pi over 2 to pi, and r will go from, what did we say, from 0 to 1 plus cosine theta of r dr d theta. Okay, at this point, it's just computational, so no big deal. We are going to split this as usual into inner and outer. The inner is going to be, well, it's a simple integral, simple antiderivative. It'll be r squared from 0 to 1 plus cosine theta. This is 1 plus cosine theta squared minus 0, okay? Cosine squared theta plus 2 cosine theta plus 1. For the outer, it's integral from pi over 2 to pi of that. Now for cosine squared, remember, if you want to integrate that, you usually use the double angle identity for cosine. So I'll box that over here. Cosine of 2 theta equals cosine squared theta minus sine squared theta. If you don't remember like the exact version to put in for the integral, you can always go and get this when you need it. So cosine 2 theta equals cosine squared theta minus sine squared theta. We then want to isolate cosine squared to have something to put into this. So we're going to substitute this for 1 minus cosine squared theta. What that'll get us is that this is 2 cosine squared theta minus 1. You then isolate to get cosine squared theta equals, you add 1 and divide by 2. It's 1 plus cosine 2 theta over 2. So that's what we can put in there. This is not integration by substitution because there's no du. You're just putting in a different version of the same thing. So this will be integral from pi over 2 to pi of that 1/2 plus cosine 2 theta over 2 plus 2 cosine theta plus 1 d theta. The 1 and the 1/2 can combine to get 3/2, and we'll take that into account with the antiderivative. This will be 3 theta over 2, so that's that term and that term, plus, and then the antiderivative of cosine is sine, positive sine. This will be sine of 2 theta over 4, because if you take a derivative, that will leave the 2 on the bottom, and then plus 2 sine theta. That's this term and this term. Theta will be evaluated at pi over 2 and pi. Put in pi, and you get 3 pi over 2 plus, and sine of 2 pi is 0. Sine of pi is likewise 0. Minus, put in theta as pi over 2, and you're going to get 3 pi over 4 plus sine of 2 times pi over 2. That's sine of pi, which is, again, 0. But this term's not going to be 0. 2 times sine of pi over 2, sine of pi over 2 is 1. So this will end up being plus 2. 3 pi over 2 minus 3 pi over 4, a half minus a fourth is a fourth. So this will be 3 pi over 4 minus 2. So what does this let us say? This lets us say that A1 is 3 pi over 4 minus 2. 3/4 of pi is like 3/4 of 3 is 2.25-ish. So minus 2 is going to be small, but still positive. So that's good. So we've got A1. Now we're going to find A3. In order to find A3, we need to get bounds of integration, first of all. So it's pretty clear that the upper limit of integration is going to be pi over 2 because we go from here up to here. But where do we start? That's the more salient consideration. Do you remember your trig? You got to find the place where they overlap. So where is it true that 1 plus cosine theta equals 3 cosine theta? We're interested in this overlap, right? We don't want to know where they intersect. If you subtract cosine theta from both sides and isolate it, then you're going to get cosine theta equals 1/2. Think about your unit circle. You know where this happens. In fact, if you think about it, you'll know that it happens not once, but twice. That corresponds to this and this, which translate into our new diagram there and there. Of course, we only want one of these because we're just getting A3 instead of getting A3 and A4 at the same time. This happens at, do you know what it is? Unit circle? Yes? Good, pi over 3. So technically, the solution to this is plus or minus pi over 3, but we're just going to use the positive so that we can find just A3 instead of worrying about both of them. So now we're finding A3. Integrate over A3 of r dr d theta. And this is going to be integral of theta. This is what we just put in so much work to get. It's going to be from pi over 3 to pi over 2. R, now this is where things get really interesting, but don't worry, it's not more work. It's just like interesting. R goes from 0 through the circle to the edge of the cardioid. So what's happening here? Well, you're going from here through a certain inner to a certain outer. Well, that means you're going to be doing outer minus inner. The larger minus the smaller. This is just like when you found area between two curves in your single variable calculus class. So it's going to be the outer function minus the inner function. The outer is the cardioid and the inner is the circle. So it will be the cardioid minus the circle. Those are the bounds on R. So I have to go and look at their equations. All right. Outside the circle, that means 3 cosine theta is going to be the lower limit of integration. And then 1 plus cosine theta is going to be the outer limit. With this programmed in, now this is going to be equal to A3. Okay. Inner is r squared over 2. Oh, you've got to be kidding me. Hang on. Wait. You probably watched in horror as I did the whole big integral there. In this part right here, you probably watched in horror as I omitted the 1/2. Well, here it comes. Because I did it badly the entire time, I can populate the 1/2 all the way through, and it simply goes a half, a half, a half, a half, and this will be 1/2 of that for a value of not 3 pi over 4, but 3 pi over 8, and not -2, but -1. 3 pi over 8 minus 1. Okay, 3 pi over 8 minus 1. Because it's half of what it was before, it's still positive. So it's still like a plausible value. All right. R squared over 2. From R equals 3 cosine theta to R equals 1 plus cosine theta. This will be 1/2 times, I'm not forgetting this time, times R squared. This is 1 plus cosine theta squared. And then minus 3 cosine theta squared. 1/2 times cosine squared theta plus 2 cosine theta plus 1 minus 9 cosine squared theta, which is, of course, 1 minus 9 is -8 over 2 is -4 cosine squared theta plus 1 cosine theta plus 1/2. And now we're going to integrate this as theta goes from pi over 3 to pi over 2. So this is the outer. I promise this is the very last part. From pi over 3 to pi over 2 of this d theta. Well, of course, we're going to need to turn the cosine squared into its more easily integrable format. So we're going to use this. So 1 plus cosine 2 theta over 2. 1 plus cosine 2 theta over 2. And so I'm just going to do that right now. -4 times that will be -2, as in -4 times 1/2. And then plus the cosine 2 theta over 2 part, -4 times that will be -2 cosine 2 theta. And then plus cosine theta plus 1/2. Well, that will turn the -2 into -3/2. So I'll just make that change right here. -3/2. Okay, now I'm ready to integrate. So this will be -3 theta over 2. So that's that, minus 2 sine 2 theta, but then over 2. So that's minus sine 2 theta, and that's that one. Plus cosine theta is plus sine theta. And this whole thing is going to get evaluated at theta equals pi over 3 up to pi over 2. Putting in pi over 2. If you're still watching this by now, then you're a real hero. Putting in pi over 2 will get us -3 pi over 4, and then minus sine of 2 times pi over 2. That's sine of pi, which is 0. So that's -0. And then plus sine of pi over 2 is plus 1. Okay, so that's the pi over 2 version. Now, the pi over 3 version. -3 times pi over 3 is pi, right? So that will be negative pi over 2. Agree? Yes? Negative pi over 2 minus sine of 2 pi over 3. 2 pi over 3 means 120 degrees on the unit circle. That's going to have a sine of √3 over 2. So this is minus √3 over 2, and almost done, sine of pi over 3 is actually the very same √3 over 2. So these two end up going away, which is kind of nice. Square roots are bad. So we end up having -3 pi over 4 plus pi over 2, because these combine. So a half minus 3/4, that's -1/4, right? Like pi over 2 minus 3/4 pi is going to be the same as -1/4 pi. And the only other thing that wasn't 0 or didn't cancel out is this. So we're going to have 1 minus pi over 4. 1 minus pi over 4. Pi over 4 is like 3/4. So just like before, this is 1 minus 3/4-ish, which is not a large number, but is at least positive. And that's what we want, because if this area ended up somehow being negative, that would be like bad. So A3 is that. So let me go back and grab what A1 was equal to. A1 was 3 pi over 8 minus 1. And what we want here is 2A1 plus 2A3, because remember, A1 was half of the portion just governed by the cardioid, and A3 was half of the portion governed by the cardioid and the circle. So really, we need to double both of them and then add them together. Well, this is going to be 3 pi over 4 minus 2. That's the 2A1 part, plus 2 minus pi over 2. That's the 2A3 part, multiplying the 2 through a set of parentheses. -2 plus 2 goes away, and 3 pi over 4 minus pi over 2, 3/4 minus 1/2 is pi over 4. And if you have gotten to the end of this video, you have the most stamina of any person in history, and you should give yourself a giant round of applause.